Oh, my parents are home. That's why. Hopefully my internet doesn't go out. I'm going to keep my video and everything off.
All right. Hey, good afternoon, everyone. I think we're streaming live now. Welcome back with another Keep Looking Up. We're happy to have you this lovely Saturday. Our show today is going to be all about exoplanets. This is one of my favorite topics in astronomy, so I'm really excited to share it all with you. We will start with a little star talk as we normally do. I'll lead that. And then our student, Eleni Hudzik, is going to talk about exoplanets and start us off with that. And then we're going to end with Dr. Patrick Durrell as he talks about some of the technology in the spacecrafts that allow us to understand and learn more about exoplanets. So I do want to start out by saying exoplanets are planets that orbit other stars that are not our sun. So keep that in mind. These are planets that are incredibly far away, further than we've ever traveled with a spacecraft, and incredibly tricky to discover. So we'll focus on that more. There's a couple of things I wanted to mention. This show will be streaming live on Facebook, but will also be archived on our YouTube channel at WB Planetarium. We're doing these each Saturday at 8, but I was invited as a guest speaker to a planetarium virtual show by a different planetarium. Next Thursday, let's see, what day is that? The 21st, I think. Yeah, so next Thursday, the 21st at 7 p.m., you'll see the event details on our Facebook because we're co-hosting it. And it's going to be all about the sky from the southern hemisphere. So these are stars, many of these stars you cannot see from over Youngstown or even anywhere in the US. And then we'll be focusing on some of the world's best observatories that are built in a South American country, Chile. And so it's going to be a really fun time. And if you want to learn a little bit more about some of the constellations and stars that you can't see from Youngstown, this is a wonderful star talk to join us next Thursday, May 21st at 7 p.m.
The event is up on our Facebook page already.
Yeah. Yep. So I guess I'll do a quick introductions and then we'll get started. I'm Tiffany Wilbrick at the Planetarium Lecturer at the Ward Beecher Planetarium. On my screen, we have Dr. Patrick Durrell, our Planetarium Director.
How's it going, eh?
We have Eleni.
Hello.
Kurt.
Hello.
Nishan. And Jenny.
Hi.
All right. That's our whole crew, y'all. Let's get started. I'm just going to share my screen here. And let me move this out of the way. Okay, so I have our sky set right now to, let's see, it's tonight. It's about 9, it ran forward just a little bit. It's about 9:20, so it's a little bit after our show will end today. Okay, I'm gonna kind of give us a north-facing view here. But if you look towards our western sky, right as the sun's going down, we're about to lose this planet, but you can see this bright, beautiful planet Venus towards a little bit northwest in our sky. Right, again, it's in our sunset, so you have to go right as the sun is setting. We won't be able to see it for in a couple of weeks. It'll probably be too close to the sun to see for a while. You can see Stellarium is showing us that Mercury is also right below Venus, but there's no chance you're going to see that. It's way too close to the sun right now. And so, but even this is about 9:30. You can see it's not completely dark yet. We're moving towards summertime. Thank goodness it's getting warmer weather outside. We aren't trapped in our homes. We could at least go outside a little bit, right? And it's been really, really nice. So part of the warmer weather and part of the summertime, it also brings longer days. So it's good in terms of being able to go outside, but it's not always so great for star viewing, because unless you're a night owl, you have to stay up pretty late to see some stars this time of year. But right as the sun's going down, you'll see some bright stars beginning to appear in our sky. I'll zoom out just a little bit here. High in our northern sky this time of year, we see these 7 bright stars that make the shape of a big spoon in the sky. That's our Big Dipper. And it's really, really easy to see no matter what level of light pollution you have. So light pollution it's created by lights that we use outside at night, like street lights, headlights on cars. If you're in a city with more people and more going on, you'll have more street lights outside, things like that. You're going to generate a lot of light pollution. If you're farther out into the country, where everything's a little more spread apart, then you might have better skies. But in either case, you should be able to see the Big Dipper, assuming no clouds. And it's useful because it can point you to this star here, star called Polaris, or the North Star, because that star always points you north. It hovers above our North Pole on planet Earth. It's just kind of like a happy coincidence that there's a star that hovers directly over the North Pole of the Earth, so that as it's spinning around, it's the only star in the sky that never looks like it moves. It remains fixed in our sky. So it's kind of like a nighttime marker. You can depend on it to always point us north. That's the case for the Northern Hemisphere, at least. You'll learn a little bit more about what the sky looks like in the Southern Hemisphere if you tune in next week. Now, we talk about the Big Dipper and the North Star a lot in our show. So something new that I wanted to add to this, if you had a telescope or even basic binoculars, or even if you had really, really good eyes and good skies, you might notice that the middle star in the handle, see 1, 2, 3 stars, that's where you would hold our Big Dipper spoon. That middle star there is not 1 star, it's actually 2. So if we zoom in a bit, here I can show you this is called Alcor. Okay, the big star here is called Alcor, and I'm sorry, Mizar, and the little star is called Alcor. I had the little star highlighted there. So Mizar is the big star that you see most visibly, but it has a tiny little star right beside it called Alcor. And this is really, really interesting to see, even through basic binoculars. It's a lot of fun. Now, if you had a higher power telescope, you might notice there's all kinds of little galaxies around the Big Dipper. This one here is called M101, and it is a galaxy that the two of our astronomy professors here at YSU have studied. They studied the outer edges of the galaxy, some of the stars in the very edge of this galaxy. Isn't it beautiful? So there's a lot of interesting things that you can see, even in the Big Dipper, if you had a little telescope. And this is, like I said, if you like to stay up late, this is a great time of year to pull out a telescope. In general, the weather is a little bit better, there's less clouds, and of course it's warmer, so you don't have to be miserable out in the cold. Okay, so a couple of other bright stars that you can see really easily, even if before it gets completely dark, or even if you had a lot of light pollution. This bright star here is called Arcturus. And the way that I find that star is, you see how the handle of the Big Dipper sort of curves or makes an arc in the sky? You can extend that arc out like this, an arc to this beautiful golden star. If you could see it in a telescope, it's really beautiful golden color. So you arc to Arcturus, and then once you're at Arcturus, you notice another bright star this way. You can spike to this star called Spica. So you arc to Arcturus and you spike to Spica. And so those are 2 really bright stars early in our evening sky towards the east. They get higher in our sky later as we go. In fact, let's do that. Let's stay up a little bit later, okay? Because even if you go out shortly after our show tonight, if you're in the Youngstown area, I know we have lots of people from different areas. Welcome. We're excited to have you. The sky doesn't change too much east and west. Sometimes it's different times. So if you're like way on the West Coast, then the sky would set at a different time like that. Well, that's why we use time zones, right, to account for that. But north and south, the sky does change a little bit. So I'm going to move forward in time to probably I don't know, 10:30, 11, let's find out. Something like that. I see it's nice and dark. And I can actually see the Milky Way rising over in the east here. Okay, let's see, what time is it? It's probably around 11. Oh, wow, I stayed up really late. 2 a.m. Let me go back a little bit because no one's staying up that late. Let's stay up till midnight, okay? Because if you do, you can see some of the summertime sky, okay? I'll zoom in here a little bit. It's really low in the eastern sky, but the cool thing about the sky is, yes, it changes over your head through the course of a night, and that's due to Earth's rotation. Earth is spinning, so it makes the stars appear, and the sun appear to move across the sky during the day, and the stars appear to move across the sky at night. But the Earth also moves around the sun in a year. So as we are moving in a month or two, we're getting closer into summertime, we're getting deeper into that summertime weather. The Earth will have moved around the sun enough that we will see more of these summertime stars earlier in the night. So in about a month or so, let's see, about a month or so, I would say about 2 months, this part of your sky will be up around 10 o'clock or so, so a little more reasonable time. But we have 3 really bright stars in our summertime sky. They make a triangle. So we call this the summer triangle. I'd love to talk about the summer triangle. There's a lot going on here, but it also cuts into our Milky Way cuts into the summer triangle. You can see that's the plane of our galaxy. The Milky Way galaxy that we live in is sort of flat. It's like a pancake. And so because we're inside looking out, we experience that as sort of this curved line in our sky. And summertime is one of the best times. If you can find dark skies, I don't know that you could see the Milky Way anywhere in Youngstown, but if you go outside of Youngstown, away from light pollution, summertime is one of the best times to see the Milky Way. As we get later and later into the summer, this Milky band of light will get higher and higher in our sky. And this part of our Milky Way that's rising in the southeast is what we call the core. You're looking into the center of our galaxy. So there's even more stars there than in other parts of the Milky Way. It's really cool. I also wanted to mention, I guess I haven't risen yet, around 1 a.m. you will see 2 planets, both Jupiter and Saturn, rising in the southeast sky. But we don't have to hang out that long to see that. Okay, what I really wanted to talk about was the summer triangle here. The bright star at the top is called Vega. I'm gonna have a question for you guys, okay? So listen up, all right? We have this bright star here, Vega. We have this bright star here called Altair, and we have this bright star here called Deneb, okay? So my question to the audience, I'll give you a couple minutes to answer. Which star is the brightest star? Is it Vega, Altair, or Deneb? Okay, you can say top, right, and left if you forget, because they're not all labeled, okay? So students, let's give this maybe a minute and then just pop in and tell me what people are saying, okay? I'll mention some of the constellations that we can find in the summer triangle while we wait for you to decide which is the brightest star. Okay, we'll zoom in a little bit here. Oh, now we have all 3 names. There we go, perfect. Deneb is in the constellation Cygnus the Swan. Okay, Cygnus is the constellation name. So this is Deneb. The word Deneb actually means tail. And so that's the tail of the swan, and then her nose comes out this way. And then there's one wing this way, and another wing that comes out this way, right? Vega here, get rid of that, is in Lyra the harp. So it's a little abstract, but this is sort of the frame of the harp, and you can imagine some strings. And then Altair is in Aquila the eagle. So you can imagine the head of the eagle. This would be the eye, the nose, the back of the head, and then the wings and the tail back here. Okay. So those are three constellations that you can, three summertime constellations that you can find super easily, because the brightest stars in each of those constellations make this big triangle in the sky. We call it the summer triangle. So students, what are people saying?
Well, I'm not a student, but we've got 5 Vegas, 2 Denebs, and 2 stars on the left.
2 stars on the left. Oh yeah, so that would be Deneb. Okay, so this is a little bit of a trick question, and it's okay if you got it wrong, because actually you all technically got it right, but then again, you kind of all got it wrong too, because we have to be really careful with what we say is a bright star. Are we talking about how it's apparent brightness? How bright does it appear in our sky? Because that would be Vega for sure, right? It looks the brightest of all of these 3 stars here. But if you talk about absolute brightness, so if you are counting for distance, these stars are different distances away from us, then it might look a little different, okay? So I probably don't have all of these exactly memorized, but Vega is about 16 or 17 light years away from us. That's a measurement of distance, okay? It takes the light that Vega is shining, it takes it 17 years to leave that star Vega and to reach us on Earth. Okay, so if you're looking at Vega, that happens because space is so big. Okay, it almost feels like a time machine because the distances in space are so vast that it takes light, the fastest thing in the universe, real time, years to travel between star systems. So Vega, in this case, Vega is 17 years away. So if you went outside tonight at around midnight and you saw Vega, then you're actually seeing a picture of that star as it was 17 years ago, okay? Because that's how long it takes light to reach us. Altair here is 25 or 26 light years away from us, okay? So if Altair is further away from us, Vega is closer to us, which star would actually be brighter? That would be Vega, right? Okay. And then Deneb here, on the other hand, is over 2,000 light years away from us. 2,000. Okay, so that means that it takes light from Deneb 2,000 years to travel from that star to us. So imagine if you brought all these stars up, equal to Vega. So Vega is the closest star. Altair would probably be a little bit brighter. Sorry, yeah, it would probably be a little bit brighter. But Deneb, if you brought Deneb as close to us as Vega, Deneb would be so bright that you could see it in the daytime. Not even our own sun would be able to wash out the brightness of that star in our sky. Isn't that crazy? So stars' brightnesses and their size can vary wildly. And Deneb is one of those really cool examples. It's one of the further stars that we can see with our eyes. And that's why it's one of my favorites. Okay, get rid of these. One thing I did want to mention, we'll do Cygnus here again. The theme of our show today is exoplanets. So exoplanets are planets that are orbiting other stars so we see stars out at night. And before 1992, when we looked up at the stars and we imagined, I'm sure many people wondered, are there planets like our planet orbiting other stars? And there were many science fiction writers that wrote stories about this, but that's kind of all it was. In 1992, that's about all it was. Okay, it was just science fiction. And then until one day, we confirmed a planet around a star. Okay, and then we started confirming more. And today we have thousands of confirmed exoplanets. And just small areas of the sky that we've looked. We haven't even looked all over yet. But based on what we've found so far, we think that planets not only exist around other stars, they're kind of common. And it seems like sort of a natural process that happens quite often. And any given star that you look up in the nighttime sky, not all stars have planets, but on average, a random star you would pick from the nighttime sky could have between 3 and 4 planets around it. That's how, to give you an idea of how common planets really are. And so what I'm going to show you now is every confirmed exoplanet in your sky. So those little green circles are circling a star that has at least one confirmed planet orbiting it. You'll learn a little bit more about this in a moment. Now you notice in Cygnus's wing there that there are a whole lot of planets there compared to everywhere else. Well, that is data bias, okay? It's not that there physically are just more planets there. There are probably that many planets everywhere in the sky, or at least in areas of the sky. I mean, there's more stars towards this Milky Band of light, so that would make sense that there'd be more planets there. But this was due to a mission that NASA had called the Kepler, is a Kepler Space Telescope. It orbited the Earth for, I mean, it's still orbiting the Earth, but it was looking at this part of the sky for 4 or 5 years, something like that. And basically it just stared at that grid, at that section of the sky, and it watched the stars' brightnesses. We've talked about brightnesses with stars today. And it just stared at those stars. It had this really, sensitive instrument that could very, very accurately detect the brightnesses of the stars in that part of the sky. And it monitored any changes in that brightness. And then the idea was that if a star became dim periodically at the same time over and over, every 4 days, every 8 hours, every 3 months, then that suggests that there is something orbiting that star that would slowly dim it out. So that was just one way that we've discovered exoplanets. You're going to learn more about that from Eleni here in a moment. But that's why we have this huge chunk of the sky with confirmed exoplanets. So if you go see Deneb and you see our swan Cygnus, know that we have confirmed thousands of planets just in that tiny chunk of the sky. Pretty cool. Do we have any questions before we wrap up with the stars?
Charles would like you to make him repeat arc to Arcturus and spike to Spica.
Okay. Well, let me get rid of these. Yeah, it's not as good in the dome, but we'll try it. All right, you ready? Do you guys remember? You use the Big Dipper's handle, and you arc to Arcturus, and then you spike to Spica. Can you guys say it with me? I'm not going to hear you, but it'll make me feel better to know that you're going to say it with me. Oh, also, students, you can say it with me. Yes, I'm making you. That's part of the torture.
Yay.
Jenny, you too. All right, say it with me. You arc to Arcturus and spike to Spica. Yeah.
Yay.
Don't forget it. All right, Eleni, I'm going to turn this over to you now. Thank you guys.
We had one more question for you, Tiffany.
Sure.
Why did they pick that quadrant of space to monitor for exoplanets?
That's a wonderful question. Because it was part of the Milky Way. So we know that more stars exist around the Milky Way. And so it seemed like a good place to look. But there's more stars, it seems like there would be more planets, right? And I think there's also, there's probably some consideration about dust, because there's a lot of dust in the Milky Way. So that might be why it wasn't like directly center, because there's a lot of other junk in the Milky Way. So I think they picked a spot that they could stare at in the Milky Way and see lots of stars at once. Great question. All right, Eleni, do you want to take it over? I'll feel free to ask more questions. I'll be in the comments, and you can ask Eleni or Dr. Norell any questions throughout the show. We love to hear from you guys. Thank you.
All right, I'm going to share my screen now. All right, so first thing, what are exoplanets? Tiffany already told you this, but in case you just joined us here, exoplanets, also known as extrasolar planets, are planets like Mars or Jupiter or even Earth, but they're outside of our solar system, usually orbiting other stars. So far, over 4,000 exoplanets have been discovered, most of them in a very small part of the sky, as Tiffany has shown you, so astronomers speculate that there are many more. Now is a very exciting time to study exoplanets because new ones are being discovered every day. The first exoplanet wasn't discovered until 1992. So just in the last 28 years, astronomers have already been able to find a lot of exoplanets and are working to discover even more. But why did it take so long for astronomers to discover exoplanets? We know that there are 8 planets that orbit the sun, and we know that there are a lot of stars that are like the sun. So doesn't it seem intuitive that there would be planets around other stars? Yes, but exoplanets are very difficult to detect. We can't really find them by just trying to spot them near other stars. Look at this picture, for example. This is a diagram that's made to show the size of the Earth relative to the size of the sun. I do want to point out that the Earth is not actually this close to the sun. This is just a size comparison. But as you can see, the sun is significantly larger than the Earth, and we also know that it's significantly brighter. So trying to find a small, faint planet next to a big, bright star is extremely difficult. Kind of like trying to spot an insect near a searchlight. There's just too much light coming from stars, which makes it incredibly difficult to directly observe small objects like planets that might exist near them. Now you're probably wondering how astronomers have discovered exoplanets if they can't even see them. There are several methods for discovering exoplanets, and I'm going to tell you about some of the methods along with a few examples. So as I mentioned, the first exoplanet was discovered in 1992. Here's a very pretty artist's impression of how the exoplanet and its star might look, but this isn't exactly how the star would actually appear. It's just an artist's impression. This was a really interesting case because it was not expected. The astronomers who discovered it weren't even searching for exoplanets and weren't using a method that's commonly used to discover exoplanets today. They were studying a very unique type of star called a neutron star. Neutron stars are some of the most dense objects in the universe, with the exception of black holes. They're remnants of massive stars that have exploded called supernovas. So no one expected to find planets orbiting these stars. However, when astronomers were studying one category of these objects called pulsars, they noticed something odd. Pulsars are known to emit pulses of light at regular intervals as they rotate, and astrophysicists have ways to predict how often the light is emitted. A pulsar was discovered that was not behaving as expected. The time between pulses didn't match the calculations that were done by astrophysicists. This behavior could only be explained by planets orbiting the pulsar, and research was conducted that confirmed these claims, making this the first time there was solid evidence of planets existing around other stars. Do we have any questions so far?
Yes.
All right.
Aspen Glassbill is asking, are the current methods we use for detecting exoplanets are they capable of detecting a planet the size of Earth?
That is a very good question. It is definitely much easier to detect larger planets, as I'm going to talk about here in a minute, but we have detected planets that are the size of Earth, which I will get to. Do we have any other questions before I go on?
Not so far. We'll keep you informed.
So like I said, this was in 1992, and around this time, a lot of astronomers were searching for exoplanets around sun-like stars. But the next exoplanet wasn't discovered until a few years later in 1995. This exoplanet orbits the star 51 Pegasi, which is a sun-like star in the constellation Pegasus, making it the first exoplanet discovered around a star that's similar to the sun. This was an important discovery because it showed that our intuition might be right. Planets might actually be common around stars like our sun. This planet was originally called 51 Pegasi b and has since been formally named Dimidium. This is an artist's conception of what it might look like. As you can see, it looks kind of familiar. It looks like a planet you might recognize. Looks a lot like Jupiter, right? So based on the mass of the planet, we know that it's very similar to Jupiter, but this was a huge surprise to astronomers because the massive planet is very close to its host star and orbits in only a few days. And based on our understanding of our own solar system, gas giant planets like Jupiter can only form far away from their host star. In our solar system, the terrestrial rocky planets are close to the sun while the gas giants are far away. This was perplexing to astronomers, but many gas giants that are close to their host stars have since been discovered and have been dubbed hot Jupiters because they're similar to Jupiter, but they're very hot due to their proximity to their star. This is one reason why it's important to study exoplanets. By looking at other systems of stars and planets, we can learn a lot of new information about planets and planetary formation that we can't learn from our own solar system. So how did astronomers discover Dimidium? Dimidium, like most hot Jupiters, was discovered using a common method called the Doppler velocity method, sometimes known as the Doppler wobble method. You may have heard of the Doppler effect before. The most common example of this effect is the sound of sirens on a police car as it drives past you. There's a noticeable change in pitch as the car is approaching you and as it's driving away. So what does that have to do with stars and planets? Well, light behaves in the same way. If an object, like a star, is traveling fast enough, then we can use telescopes and other astronomical instruments to detect changes in the light based on how fast it's moving relative to us. Hence the Doppler velocity method. The star's gravity is pulling on the planet. So here's a visual. So think about how a planet orbits a star. The star's gravity is pulling on the planet, keeping it in orbit around the star. But the planet's gravity also pulls back on the star. So this is really exaggerated. The effect is a lot more subtle. But rather than having a planet just going around a star that's directly in the center, the star, shown by the yellow object here, the larger object in the center, and the planet, the blue object, are orbiting a common center of gravity. The star is moving in a tiny circle, and therefore it appears to wobble. If we're looking at the system at a steep enough angle rather than a head-on point of view as shown here, we can detect this subtle motion using the Doppler method to analyze the light from the star as I described earlier. And that tells us that there's a planet orbiting the star because that motion would not exist without influence from a planet's gravity. This effect is much greater by a massive planet that's close to its star. So that's why this method is useful for finding hot Jupiters.
I got a couple of questions for you, Eleni.
Yeah, go for it.
Matthew Commons would like to know, is there a reason there was such a large gap between the discovery of the first and second exoplanets? Is it due to something like a new method of searching, new technologies, or something else?
So I don't know the exact answer to that question. I know that the reason that we've only started discovering them so recently in the last 30 years is because the technology has to be extremely precise. These are really subtle differences that we're looking for to find these exoplanets. And the first one, as I said, was discovered completely by accident. I'm sorry, I don't have a better answer for that. Anything else?
The other two, I think, will be coming up later in either your talk or Dr. Durrell's, but George Hunsick would like to know, will the James Webb Space Telescope be used for any kind of exoplanet detection? And Alan Glasspool wants to know, are we capable of detecting or determining if an exoplanet has oxygen-rich atmosphere or life forms generating oxygen on that planet?
All right, so as for the first question about the James Webb Space Telescope, Dr. Durrell is going to tell you all about that in a couple minutes. And then here I have the other question here. Are we capable of detecting or determining if an exoplanet has an oxygen-rich atmosphere or if life forms? Okay, so I'm going to tell you about another method in a minute that we know can help us learn about the atmospheres of exoplanets. As for life forms, we can't tell. They're too far away to determine, I guess, how the oxygen is there. All right, so getting on to the next thing, the most common method for discovering exoplanets, which is also my personal favorite, is called the transit method. The first planet that was discovered using this method was found in 1999, and this has since become the most common method for detecting exoplanets. So in this method, astronomers measure the amount of light emitted by a star, and as the planet passes in front of the star or transits the star as shown here, a certain amount of light is blocked. This happens periodically as the planet orbits the star, so it's a very good indicator of the presence of exoplanets. One major disadvantage of this method, though, is that the system between the planet and the star has to be at a very specific angle for the planet to appear to make a transit. If the planet, say, was up above the star or below the star, we wouldn't see that transit and we wouldn't be able to detect the planet this way. So this limits us to observing only a fraction of exoplanets like this. However, it's still my favorite method because we can learn a lot about exoplanets by looking at their transits. As you can see, the brightness from the system appears to dip over time. And the size of this dip tells us about the size of the planet relative to the star. Additionally, if the planet has an atmosphere, the astronomers can analyze light from the star that passes through the atmosphere of the planet to learn about the composition of the planet's atmosphere. We can even use this method to learn about the distance of the planet from its host star, since the time between transits tells us about its velocity. If we know the distance, we can estimate the surface temperature of the planet as well. Finally, if the planet's large enough, we can use the Doppler velocity method that I mentioned earlier and combine it with the transit method and determine the planet's mass. And since we already know about the planet's size, we can estimate its density, which tells us a lot about its composition. That's why, to me, this method is really cool because we can learn a lot about exoplanets even though they're so far away. Do we have any questions? Any more questions?
Yes, we do. Give me 1 second here to get down to it. I was looking at another part of the comments. Charles Wyatt would like to know, do we have an estimate on the distance between the furthest discovered exoplanets and here?
So I do not know the farthest, but I do know the closest. The closest discovered exoplanet is actually orbiting the closest star to us, Proxima Centauri, which is about 4 light years away. Do any of you guys know the farthest exoplanet? You guys can chime in because I don't know it.
Yeah, I don't know. I'm kind of with you, Eleni. I think that the closest exoplanet is a whole lot cooler than the furthest exoplanet.
All right.
One other question here too. Does light pollution from Earth make it more difficult to use the Doppler method?
So all of these methods that we use the ones that I'm talking about, we use space-based telescopes for. So they are outside of Earth's atmosphere, so we don't have to worry about light pollution. It would be very difficult to see something like this from Earth. I think the transit method has been at least confirmed from Earth. I think the Kepler Space Telescope, as Tiffany mentioned, looks for this first, but we can also see it using our telescopes, but it's a lot more reliable from space-based telescopes where we don't have to worry about the atmosphere or light pollution.
I will chime in a little bit. Our one astronomer at YSU, Dr. Feldmeyer, was with a project that used a telescope out in Arizona before they launched the Kepler telescope, and it looked at that section of sky Tiffany showed, and they looked for possible candidate stars that might have planets, and those were some of the first ones that Kepler pointed at. It turned out, I think they found 10 possible candidates, and at least a couple of those proved not to have stars, but I did not hear the final count of how successful their quote-unquote scouting mission was.
That's awesome.
I thought I remembered they had like 3 candidates and then one of them was confirmed.
Yeah, that is correct.
So one of our astronomers was on a team that discovered an exoplanet. It's as cool as it sounds.
That is awesome. I didn't know that.
Yeah, anytime you talk to him about it, which he was going to be on our show next week, so if you guys want to talk to him about it, you can. But anytime we bring it up, he said, I would not recommend it. I guess it was a lot of tedious work.
Uh-huh. Okay, so next thing. One famous system containing exoplanets is called TRAPPIST-1. TRAPPIST-1 is a red dwarf star, so it's quite different from our sun, but 7 planets have been detected around TRAPPIST-1 using the transit method. This is an artist's impression of what the system might look like. The planets are named TRAPPIST B through H and are labeled here. We know a lot about these planets since they transit their host star. We know that all 7 of these planets orbit their host star much closer than Mercury orbits the sun, but because red dwarf stars are relatively cool, most of the planets have mild surface temperatures. Another cool thing, because these planets orbit so close together, if you were on the surface of one planet, you would be able to see many of the other planets in the sky, and some of them would appear larger than the moon appears from Earth. Most of these planets are similar in size to Earth, and 3 of them, TRAPPIST-E, F, and G, lie in what astronomers call the habitable zone, also known as the Goldilocks zone. Conditions at this distance from the star are just right for liquid water to exist. So why do astronomers care if planets are in the habitable zone or have liquid water? Obviously, these planets are much too far away for us to visit, but 30 years ago, we weren't even sure if planets like Earth existed around other stars. And now we know that they do, and we continue to learn more about planetary systems this way. So as I mentioned, over 4,000 exoplanets have been discovered. This plot from NASA's Public Exoplanet Archive shows the cumulative number of exoplanets that have been discovered as of May 8th, 2020. Some of the methods are shown on the left. We talked about the first 2. As you can see, the majority of exoplanets have been discovered using the transit method, and many have also been discovered using the Doppler velocity method, labeled as the radial velocity method here. So you can see in 2014 and in 2016, we had huge jumps in the number of exoplanets we knew about. That's thanks to the Kepler Space Telescope. During those years, large amounts of data were released from that telescope. So that's why you see those big jumps there. But I don't want to get too into telescopes because next, Dr. Durrell is going to tell you all about a telescope that will look for exoplanets in the future. But before I wrap up, does anyone have any questions? Any more questions?
Students, did you guys see any questions?
I have shared all the ones I have seen.
Did we ask Aspen's question, has tech improved for detecting if exoplanet atmosphere has life-creating oxygen or carbon dioxide?
Sorry, can you repeat the question?
Sure. Has tech improved for detecting exoplanet atmospheres that have life-creating oxygen or carbon dioxide? I think that that's a topic that Dr. Durrell is going to be discussing at length, and it's has a really, really great answer. So I think we should let him take that one.
Cool.
I do have one last one for you, Eleni. Is the Goldilocks zone range estimated based on life being carbon-based?
So it's based on the temperature of the planet, based on whether the temperature range is where liquid water can exist. So it's not too hot, it's not too cold, it's just right. If it's too cold, the water's frozen. If it's too hot, the water evaporates. So that's why they call it the Goldilocks zone.
And that's important because we have exactly one data point for a place that holds life, and that's Earth. And all life on Earth has one common ingredient, and that's liquid water. So finding a planet that has a surface temperature suitable for liquid water on its surface is a really good place to look for life that would be somewhat similar to life on Earth.
All right. So if that's it, I will stop sharing my screen and hand it over.
Okay. As usual, it's always tough to follow Eleni, but I'm going to give it my best shot. I just want to tidy up some of the things, and some of these are going to be related to some of the questions that we've already been getting. Because one of the things about studying exoplanets is we can sort of start looking at some of the big questions that people have always had. And some of these have already been touched on. You know, how common are planets? I mean, we're now finding that planets are a natural part of star formation. There's nothing special about our sun as far as making planets. You know, what kind of stars have planets? Little red dwarfs, normal stars like the sun. I mean, again, the number of planets in the Milky Way alone could be staggering. If you were to just assume that every star had one planet, this is just throwing a number out there, there'd be a couple 100 billion planets in a Milky Way galaxy alone. So there's a lot of them out there, and as Eleni mentioned, it's tricky to find them. But of course, it always goes into the idea: is there life out there? Are we alone? What are the signatures? How do we find life? And that's certainly one of the end games of it, but we're still not there yet. Now, as mentioned, exoplanets are a hard thing to find. Okay, that with the precision needed to find them with any of the techniques, transit method, microlensing, the Doppler wobble, all require high precision observations. And this little graphic is what Eleni was mentioning earlier, that, you know, the direct method, what I sometimes call the brute force method, which is, can we just stare at a star and look for planets around it buzzing around like bees in a hive? And the answer is, in a few cases you can, but most of the times you can't, because the star clearly outshines the planet by a lot. However, one of the things that people are going to be using in the next generation of telescopes is that in the infrared, planets emit their own infrared radiation, and that includes the Earth. So planets are a little brighter, you know, in contrast in the infrared. So the infrared is a way to go hunting for planets a little more effectively. But we have done it from the ground. I mean, this is a little video of a bright star using ground-based telescopes, and you can see some objects clearly in orbit around it. So these are actual images of exoplanets. Now again, only about a dozen or so have been discovered this way. So this is not the reliable way to find them. Again, see all the stuff that Eleni talked about for the most successful techniques. Now, of course, the transit method is the big one now. And the idea is, can we go beyond the Kepler space mission? What's the next way? How do we find more and more planets? I mean, we found 4,000. You think, oh, astronomers, aren't they happy enough with this? And the answer is no. We wanted to find out more about planets to help us understand not only other planetary systems, but to give more of an appreciation of our own planetary system. Now, Kepler and the Kepler field that was mentioned earlier by Tiffany and Eleni, again, was a space telescope that operated for a few years, and it pointed at one very specific spot in space. And the goal was to measure brightness variations in over 100,000 stars simultaneously. And you need to study that many stars simultaneously for this transit method to work. So the next generation of telescopes are going to improve upon that so we can find even more systems.
Dr. Durrell, we got a question.
Sure, shoot.
Why do planets emit an infrared light?
Because that's the temperatures of most exoplanets, like the Earth. The Earth emits temperatures that are, you know, just a little bit below room temperature. That's the natural emitting temperature of the Earth, because it warms up and it radiates infrared. So at temperatures of a few hundred degrees Kelvin or a few degrees Celsius, above 0 Celsius, that's at infrared wavelengths. So stars are a little dimmer in the infrared and planets are a little bit brighter in the infrared. So you can sort of play the better contrast game by going into the infrared. Now, there's a lot of different things, information we can get. I mean, the first 20 years of exoplanets, there's a lot of it has been focused on finding the exoplanets. Now, what can we do with them? The next phase of astrophysics is, what can we learn from transiting exoplanets? We can learn how big they are by watching the transit, how long it takes to go from, you know, not transit to transit. We can actually calculate the physical size of these exoplanets. We can actually understand the temperatures of them by studying the transit itself. Okay, so these are things that we can start to learn about exoplanets. That's why we can talk about hot Jupiters. It's because we have an idea of what the temperatures of some of these things can be. For example, the first exoplanet, 51 Pegasi b, when it was discovered, they predicted the temperature is about 2,400 degrees. So no, not hospitable to life in any form. Now, right now, the Kepler was shut off shortly a while ago, so it's not operating anymore. Yes.
On the other extreme there, can we detect ice planets like Pluto? And do they
No.
in infrared?
No, not really, because the problem with Pluto is that not only are they much colder, they're also a lot smaller. And the orbital period of Pluto is 248 years. So if an astronomer on another planet far away was looking at our sun, they'd have to be at the right angle and to see a transit, and they'd only see one transit every 248 years. So finding Plutos would be exceptionally difficult to do. It's hard enough to find Earth-like planets. Jupiters are easy to find. Mini Neptunes, not so bad. Earths are really hard right now. Anything smaller than the Earth is a little bit outside of current technology. But that's changing all the time. Right now, there's a mission that's actually a follow-up to Kepler. It's called TESS. It's the Transiting Exoplanet Survey Satellite. Here's an artist's rendition of it. It was launched 2 years ago. And this is another space telescope with a very specific mission. It's going to survey almost the entire sky from space, and it's going to be watching most brighter stars over the entire sky to look for transiting exoplanets. So it's kind of like Kepler with an attitude, all right? And they're planning to study, over hundreds of thousands of stars with it. And as of the other day, there have already been 46 confirmed exoplanets from TESS itself. And it's got a 2-year mission, primary mission, but I'm sure there's going to be an extended mission, or at least I certainly hope so, to keep looking. So that's the one that's currently going at the moment. And it's got a much bigger field of view. This is actually a first light image from late in 2018, and it could survey huge swaths of the sky. So instead of concentrating on one spot like Kepler, TESS is much more of a wide angle instrument. So you're going to be hearing more about discoveries, and after the first 2 years, I can't wait to see how many. I think there's lots of candidates, but confirmed ones are at 46, but that number I'm expecting to jump quite a lot in the not too distant future. Now, of course, the big telescope that's it's on everybody's mind, including mine, is the James Webb Space Telescope. And it's still planned for launch next March. I haven't heard anything about any further delays to it. But this is a much larger telescope than Hubble. It collects more light, but it's also optimized for infrared observations. So one of the key science goals of the James Webb Space Telescope is the study of planets.
Here's another question for you along those lines too, Dr. Durrell.
Yes.
Is there a better location to place space telescopes to study space other than Earth orbit? Good topic for here.
Well, actually, a good example is the James Webb. It's going to be out at a location about 1 million miles behind Earth called the Lagrangian Point 2, or L2. So it will not be orbiting the Earth. It will be orbiting the sun in a stationary point relative to the Earth. So it will stay with the Earth, but it's not going to orbit the Earth because it's optimized for infrared. Infrared from the Earth would actually cause a lot of background problems for it. Matter of fact, in this diagram you see here, this big weird thing underneath the telescope is a huge sun shield to block light, just like you use your hand to block sunlight, when you're walking or something like that. And because, we're going to be studying temperatures at, hundreds of Kelvin. So you want to reduce the effects of, say, the Earth. So you don't want to put James Webb in orbit around the Earth. So that's one of the caveats. If you want to study in the infrared, you really need to cool things down to find things. So here's just a size comparison of the mirror of James Webb compared to Hubble. So you collect 6 times more light just like that, and then optimized for the infrared. Now, James Webb will be able to find more exoplanets, but really one of its primary science goals is the next step, which is, as asked in an earlier question, to characterize the atmospheres of some of these planets. Now, these techniques have been used in the last 20 years using Hubble and some other telescopes, but the James Webb Space Telescope has got a much wider wavelength coverage. And the idea is to do what's called transmission spectroscopy. When a transiting planet passes between us and its star, some of the light from the star will pass through the atmosphere of the planet. So the atoms of some of the molecules, some of the molecules in the atmosphere will absorb light before it gets to us, and we can characterize that. Now, again, this has been done for a number of stars using the Hubble Space Telescope, but this is going to be one of the things that James Webb really cleans up on, okay? And we can find out what gases, or at least some of the gases in an atmosphere. Now, the main ones, and again, we have to look at infrared wavelengths. What molecules can you detect with James Webb? There's a number of different lines, sorry about that. A number of lines of water vapor will be accessible. So we'll be able to tell if there's water vapor in an atmosphere. Carbon dioxide will be able to tell, and even methane. Okay, so these are some of the molecules that we find. Now, not necessarily, just because it has these things does not necessarily mean there is life. But the idea is to characterize atmospheres. How hot are the atmospheres? What materials are present in the atmospheres? And then we can start thinking about biosignatures. Is this stuff could have been caused by life or not? But these are sort of the questions that people will start to do once we get more information. So, you know, again, starting from 1992 with finding exoplanets, with James Webb, we're going to actually be able to start characterizing planets. And I can bet that TRAPPIST-1 that Eleni talked about is going to be one of the main targets for James Webb. James Webb is big enough that you might be able to detect some of the materials and atmospheres in the planets orbiting TRAPPIST-1. So you're going to hear a lot more about this in the coming years from James Webb, because it is one of the key science goals of James Webb is to characterize these atmospheres. Okay. And finally, I just want to do a plug for yet another space telescope. This is a next generation one that people are already building. It's the next big space telescope after James Webb. It's called WFIRST. It's hopeful for a launch in 2025. I don't really believe launch dates this far out, but let's try and be optimistic here. And it's going to be another Hubble-sized telescope, but it's going to have a lot more field of view, and it's going to look for more planets, both with the direct method and this diagram up top using microlensing. So when a planet passes in front of a star, even if you can't see the transit, because of the effects of light bending, okay, based on Einstein's theory of general relativity, you get a brightening of the star ever so slightly by a planet passing in front. And that's another technique you can use to finding exoplanets. So WFIRST is going to be another big exoplanet hunter, although this telescope, like Hubble, is going to be used for all sorts of other science. It's not like Kepler, which is dedicated to specifically to exoplanet science. So this was just to give you a little bit of a feel for some of the stuff coming up. Like I said, we've now gone past just finding exoplanets, so we're going to start finding out more about how dense they are, what atmospheres they have, what temperatures they have. So lots of neat stuff coming up. If there's any questions, I'll certainly happy to field them. Or
well, let's see how you do with this one.
Okay.
Alan Glaspel is asking a little bit of a sci-fi question. In theory, if you have a telescope near an exoplanet and the telescope near Earth, if the lenses of each telescope were quantumly entangled, could you look into the lens of one telescope and see what the other telescope sees?
That's a good question. I never really think of it in terms like that. People do talk about interferometry of satellites, where you actually have to basically point lasers from satellites at each other and line them up. So technically you can do that kind of thing. Not so much for quantum entanglement though. But yes, you do have to be able to point. Some of these experiments you do need to have precision pointing, and they're talking about missions like that.
All right, I don't know if I'm seeing any questions, but you guys were full of wonderful questions tonight. Thank you so much.
Yeah, lots of good stuff. Yeah, exoplanets are one of those really neat things. When I was in graduate school, when I started graduate school, exoplanets hadn't been discovered, so this wasn't even an area of research. And now, well, look at it now. So,
Yeah.
just amazing.
All right. Well, that concludes our show this week, but now's the exciting time where we announce our show for next week. We did post the event a little bit early, so if you've been watching our Facebook, you already know this. Next week's show is called The Life and Death of Stars, or The Birth and Death of Stars. I don't remember. But we're going to be talking all things
Life and death.
The life and death. Okay. We're going to be talking all things stars, and because stars, as we were talking throughout this show, even stars look a lot different. They can have different colors. They can be incredibly different sizes, and that means different things for their lifespan. So we're going to be learning a little bit about that, and then we will end the show with Dr. Feldmeyer, who is our other astronomer on campus, and he's going to be talking about an area of research that he's been doing for forever, and that's planetary nebulas, which you'll learn all about. It's not really a great name for what it is, but you'll learn all about it next week. And I'm really excited for that show. If you really want to see another show, if you can't wait till next Saturday, or if you are really interested in seeing the stars from the Southern Hemisphere, tune in with us on Thursday night at 7, and we'll get to see some of that. Okay? That was everything, right? Yeah, I think that's it. So thank you all so much for another wonderful show.
Your
And
Chilean show. Mention your Southern Hemisphere
I
show.
did.
I'm sorry, I wasn't paying attention.
Yeah. Thank you guys so much for another great show, and remember, keep looking up.